In this math counts preparation, we are going to be talking about geometric probability. So let's get started. Now we're going to do a little bit of a recap with some probability. The last probability lesson in the math counts preparation video series was my hour-long video on combinatorics and probability. So if you want to watch the probability part of it, you can go ahead and do that. But we're just going to go ahead and dive into general probability. And as I said, you should always watch the videos in at least somewhat order. In this video, I'm giving you a prerequisite. Watch the combinatorics and probability video. You don't have to watch the entire thing, or you could if you wanted to. It would help a lot because a lot of probability is counting and stuff like that. So yes, so probability. So probability is basically the number of the favorable outcomes divided by the. So basically, the formula is favorable over possible. And this should make sense to you why. And I'm going to give an example. Like if we have a coin, a fair coin, and we want to flip the coin one time, and we want to find the probability that we get heads. Right, so on a coin, side 1 is going to have heads, and side 2 is going to have tails. That's just how a coin works. And if this is the same coin flipped once, what is the probability that it's heads or tails, either one? Well, let's go with heads. So it's probability that it's heads. Well, the probability that it's heads is how many chances do we have? We have 2 chances to get heads. And there's only one possible chance to get heads if we flip it once. So there's 1/2. And this satisfies our formula. You should not need to memorize this formula. It's obvious. Okay, no cramming. There's no cramming in math counts. It's all about knowing how to apply the formulas and knowing how to use them. Always know how to use a formula before you actually use it. But that's probability. Now, you have to know the basics of counting. I'm assuming you know the basics of counting, but if you don't, we are going to go over basic permutations. Again, if you did not watch the probability and combinatorics video, you will not understand the problem as much as you would if you knew how to do counting, etc. But this video is geometric probability. You should know probability, okay? I'm not relying on the fact that we're only talking about probability. This is just a recap because you should have watched the other video. Okay, let's move on. So, probability, that's basic stuff. Like, let's say we flip a coin more times. So we flipped it 3 times. We flipped our same coin, but we this time flip it 3 times. We want to flip more. Now, first off, we have to compute the possible outcomes. Okay, each time we have 2 outcomes, heads or tails, right? Now, if you're good at counting, and you should already know this, this is just 3 times 2 cubed. The answer is 8. I mean, the favorable outcomes, or the possible outcomes is 8. The possible outcomes is 8. 2 cubed is 8. Flipping in 3 times. If we flip it 3 times, we have the same possible outcomes for each coin. Right, here we have 2 choices, but then we go over here, we have 2 choices. Now we're going to multiply them because this, 2 choices over here, and this, 2 choices, so that makes 4. 4 to choose from. Now we can do the same pairing thing here. Each, and this is not every single permutation of it, but each of these can be paired with any one of these. So this is just, we can just do 2, 2, 2, 2. 2 times 4 is 8, and that gives us that. Now, we want to find the probability that, we can do lots of things with this. We can find a probability that tails is at least, let's say tails is at least 3 times. So if we want to find the probability that tails is flipped at least 3 times, how are we going to do this? At least 3 times. I want you to think about this for a minute. Alright. So tails is at least 3 times. Well, that's this outcome. It could be this outcome, or it could be this outcome. We're going to split this problem into cases. If we only have t, 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 there's only one permutation of t, 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 since they're all the same. Now, t, 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 h, we should know how to order this. You should know your permutations. Take the number of letters, slap a factorial at the end. We have 4 factorial. Divide that by the number of ways you can order the repetition. Factorial ways. Now we have 24 divided by 6. Now we have 4 for this, 1 for this. 4 plus 1 is 5. We have 5 over 8 probability that at least 3 of the flips are going to be tails. And that was using permutations. You should already know your word ordering permutations because you should have watched the combinatorics and probability video. Alright, that's another practice thing. Let's move on to the problem. Okay, a target consists of concentric circles of a radii 1 centimeters, 2 centimeters, and 3 centimeters. The innermost circle is colored red. Okay, so this right here is red. Outer ring is colored blue. The middle ring is colored white. Okay, we got red, white, and blue. And if a point is chosen at random on the target, what is the probability that it lies in the blue region? We have to remember that the blue region is the outer region. So I'm going to label this right here. The blue region is all of this. All of this stuff. All of this stuff belongs. And that's good enough. We don't need to draw a full out diagram of this color, but that's a blue region. And I'm going to label the other ones as well, just so that we don't get confused. This entire thing is red. And that's obviously white. So now we have our diagram colored. Let's leave it at that. Now, what is the probability that if we choose a point, it lies in the blue region? Well, we have a 3 concentric circle. We have some 3 concentric circles with radii 1, 2, and 3. Now, probability that lies in the blue region. Well, you might just go ahead and think, in this circle, in the biggest circle, the radius is 3, right? Radii 1, 2, and 3. The outermost circle right here has a radius of 3. And you could just say, well, the possible outcomes can be counted by, let's say, we can count the possible outcomes of this by maybe listing them out, or maybe throwing this on the coordinate plane. Maybe trying some coordinate bashing, like we could try coordinate, but then remember that would only give us lattice points. Lattice points, we don't well, in this problem, the reason this is hard to count the possible outcomes, or as of right now, is because we can have fractional points. For example, this is not true necessarily true, but this can have coordinates of, I don't know, like this can have coordinates of 1.2164, and it can also have, the y coordinate could be like we could have these weird points and we can't count all of them. They're infinite number of points. And this is where geometric probability comes in. This will not work out. And this is a classic geometric probability problem. I want you to think about how we can count in this problem. But now we're going to learn the basics of geometric probability. And it starts best to look at a problem. Now, geometric probability, we have some things that we can't really count. For example, numbers between integers like 2 and 3. If we want to find like numbers between 2 and 3, we can't really count that. I mean, all the numbers between 2 and 3, they're infinite numbers. We can keep adding zeros and ones and decimals, and it gets too much. So whenever we have problems like this with geometric representations, especially in this one, this is clear we're going to use some geometric probability. How can we measure all of the points that lie on the largest circle which contains each of the smaller circles? How can we measure that? Well, all of these circles lie in this big circle right here. They lie on the largest circle we have. And all those points lie in the circle. We can measure the amount using area. Area is what we use in geometric probability. So we can use this area to find the probability. And that makes things a lot easier. The first thing we're going to do, we're going to remember area formulas. If you don't know your area formulas, here they are. And we're going to need these in other further on in the geometry lessons. So first off, circle, that's what we're dealing with. And I'm going to go for area because we have not started 3D geometry yet. So the area formula circle would be pi r squared. Triangle and this. The area of a triangle now there are multiple ways to find the area of a triangle. You can use trigonometry, you can use multiple things you can use, but the most simple formula is just half of base times height. You could use a shoelace formula for coordinate geometry and like analytic geometry and coordinate bashing, but area of a triangle is half base times height. That's the one you're going to use. Circle, triangle, square, this is like basic, so all parallelograms. And if you are participating in Math Counts, you must at least be from 6th grade to 8th grade, so you should already know all of these. And there you go. Those all the formulas you need. Trapezoid, I often use trapezoid. So the area of a trapezoid can be denoted by summing the bases. Right, we take the sum of the bases, and then we take the average of the sum of the bases, and then we just multiply by the height. But we don't need that for this video. Now let's get into the problem. We have a geometric probability problem. That means we are going to need area. So that's how we're going to measure this figure. We're going to measure it using some area. Now let's get into this area. So first off, we have a large triangle. A large circle. A large circle that goes all the way like this. This is our large circle. I should fix that circle. So our largest circle, this radius 3, all of the points lie inside of the area of this. So that means this middle circle, which is colored white, also lies within the area of this, and this red circle also lies within the area of this. So we need to measure the area of this. Now that's just pi r squared. We take pi multiplied by the radius, but we need to square the radius. Square the radius, 3 squared is 9. We get pi times 9, which is 9 pi. Now our biggest circle, is 9 pi. Now, how are we going to get the area of this portion right over here? How are we going to get the area of this? Now, to get the area of this, first we can start off with the area of the big circle. We can start off with this 9 pi that we have. And also we've also counted our possible outcomes. So I'm going to create a fraction there. We have 9 pi, and now we need to measure the area of this blue region. Well, we don't really have any formulas to compute the area of this weird ring shape, but we can take the area of this big thing and then subtract off the area of the white circle. So if I start with this and I cut a hole in the circle, I'll be left with this tiny ring. So if I do this and I cut this out, the only thing that'll be left is the thing I want, this piece right here. So that's what we're going to use. We're going to find the area of this white circle, which also contains the red circle. So now we need to find the area of the white circle. The white circle has a radius of 2 pi r squared. Square the radius, we get 4. Multiply by pi, we have 4 pi. And this will give the area of the blue part that we want. 9 minus 4 is 5. We have like terms, we get 5 pi. We've counted the favorable outcomes. So now we have 5 pi over 9 pi. The pi's just cancel. And we are left with 5/9. And that is our answer. And this goes for all geometric probability problems. We measure it using lengths. And I'll write down the trapezoid formula. So you take basically a plus b divided by 2 times height. Okay? And basically in geometric probability, we want to measure what we want using something. Like if we have a number line, we want to find like we can use a number line, we can use probability, and we can use a lengths, right? So if I have 1, 2, 3, 4, right? And I want to measure the probability that any random point that I choose is closer to 1 or 2 than to 3 or 4, well, I can start by finding the length of this, right? And if I'm given that the length of each segment, each piece, or this is 2, and this is 2, and assuming it just cuts off over here, this is 2, and if this is 2, and the entire thing is, let's say, like 4, or 6, the entire thing could be something, each piece, and I can draw a midpoint. That's a better representation. The entire length is 8, right? And the entire length is 8. And the probability, this is the midpoint, right? And the probability that the point is closer to 1 or 2 than to 3 or 4 is we just take the sum. And that's 4/8. And that's 1/2. And geometric probability appears in all levels of math counts. Alright, you'll find it in school level, state, chapter, nationals, okay? And you'll come in all parts of the competition. You'll find it in the school level, the state level, all parts. So that's geometric probability.